Good afternoon once again. The second presentation name is Reliability Methods in Network Engineering, but it can be actually applied in any kind of engineering purposes. First, short introduction about probabilistic and reliability methods. So when we perform some engineering analysis, we have some input variables like, I don't know, strength of the material, loads, and so on, so on. And we always know, especially in structural engineering, for example, for concrete, we have some certain design strength, but we always know that you're taking a lot of samples. You do actually the statistics of your during the construction works. That's certain specimens, certain are below the design level, some above, and some kind of mean value should fall into the design value. So this is one kind of material uncertainty. Another is when we design on some loads, statical dynamics, we always do some kind of, I don't know, assumptions. When you do design this slab for a people, for the operation load, we assume that this is like 5 kilonewtons per square meter, something like that. This is some kind of approximation. We always know that there is some kind of uncertainty in that analysis, and our output of our analysis, like safety factor of, I don't know, some damage or failure, is also in deterministic value. Is deterministic value, single number, like safety factor is 1.5, but actually if we do treat the input values like loading distribution values, like normal, log normal, then we can also, the results of our engineering analysis can also be some curves that have some certain probability distribution. So this is generally the probabilistic way of thinking, and it mainly in civil engineering, for example, in the hydrology are mainly the guys that do flood risk and so on. They mainly talk in terms of, I don't know, 100-year flood or 500-year flood return periods. So, but nowadays, even in structural engineering, especially in the earthquake engineering, the new design codes like Euro codes, they demand from us to design the building to resist 475-year return period earthquake. So the more our inputs are, we quantify the uncertainties, the outputs and the results should be not the single point value, but the sum distribution, probability distribution curves. Then we can, for example, the insurance agencies or also society demands from us to know what is the risk. Especially you have nowadays in Serbia some crashes of some public buildings. So it is very useful. From the engineering purposes, it's just you need to fulfill the code. The minimum factor of safety is, I don't know, 1.5, and we obtain 1.6, and we are good. We are above the. But generally, the step above and with these all numerical values and all this modern technology, we are able to to come one level up and to speak in terms of probabilistic outcome for our analysis. And there are several numerical approaches how to treat and how to compute the some failure, some safety index according to input values. So when you have a different input value that is certain, and you combine them with some engineering analysis, then the mistake multiplies, so you have multiply one mistake by one, and you combine them, then the outcome is not pure enough. So first way is you always have some limit state function. I don't know, for example, the bearing capacity, I don't know, of this column or something like that, and you simply by integrating the formulas for the stability, we can make inverse of the standard normal cumulative probability can lead us to have some we take into account the coefficient of variation of the all input parameters, and we do some kind of graphical presentation of limit state function of the failure. And so everything on the one side is good, and everything on the other side is not good. So this is the way how we can actually integrate like our limit state function and see, but obtain results if we fall down. But it actually is not one analysis; it is multiple analysis we perform, where our results are falling down. So this is in some, for example, this have application in reliability, first order and second order reliability methods in earthquake engineering, where we have explicit limit state function. We know what stresses are making our structures to collapse, and it's easier. In some under analysis, it's not so easy to make it. Monte Carlo simulation is different approach. It's actually the iterative way of repeating the deterministic analysis. It's like we do old-fashioned way with the single point values of our analysis, and we run it enough times, and then we do some kind of statistics of all performed analysis. This is the disadvantage of this approach, because as we see in the last presentation, the dynamic analysis are they are demanding from the computation viewpoint. So they are time consuming. To perform one advanced numeric analysis, it can be one night of the calculation of some good PC computer, and you need to do it, I don't know, hundreds of times. So it is one single analysis will last 1 month. So it's not so in practice good to apply it. And generally, whenever our limit state function is not good to apply, the Monte Carlo simulation can be good replacement, but we need to select wisely the number of the simulation we need to perform. And now we come to the real application of this. Nowadays, there are very big mining projects in Serbia, and one interesting topic is the tailing dam, the slope stability of the mining pits, and the performing probabilistic analysis in this manner can be very, very applicable. For example, in this particular case, we can apply displacement-based methods. What does it mean? Whenever the displacement is above the 300 millimeters, 30 centimeters, it's quite big, but the mine pit is also very, very big. We can consider that slope fold. This is criterion for the failure. So we do like displacement analysis on mining pit, and we see what is the probability that the calculated displacement is above this threshold we define. First, important, this is also dynamic analysis. We also have this kind of frequencies. We have some rough estimation of the dynamic properties of the soil and the below ground, and the generally idea is to avoid the resonance to the level, for example, of our, I don't know, loading from the earthquake or from the equipment, from the machinery on the mine, fall in the resonance with the dynamic characteristics of our embankment or our mining pit. So this is some kind of failure modes, the slope mode that can occur in this particular case, and some ways to numerically the frequent characteristics of the mining pit. And this is some kind of way of different analysis. Is it static stability, pseudo-static stability, when we just perform the multiplies the static loads with some single coefficient, and that's how we simulate the dynamic loads. And this is the list of random quantities we take in our account. It's actually the level material properties and geometry. For in mining pits, it's not so the predefined, is it the inclination is this like this. So we also have certain uncertainties of the geometry. In mechanical engineering, probably because everything is in millimeter, is not so kind. But in mining engineering, you have all certain geometry variation and geometry uncertainty. So this is the outcome of these results. We did static and seismic stability. For static stability, the criterion is that the factor of safety is below 1. When it's below, then my pit is false. And for the seismic stability, the threshold is 30 centimeters, 300 millimeters. And this is the probability of failure in 50 years and 250 years. And actually, our design code for the mining, for structure design, don't demand such kind of analysis, but it is very good for the insurance companies, for the clients who want such results, for the society who wants to know what is the risk of these public projects or some private project that can affect, for example, some mining pits are dangerous and risky from the flooding issue. If the floods and the rainfall found, then the slope of this landfill can move. So in order to conclude, as I said already, the reliability approach and the probabilistic analysis are very applicable in the earthquake engineering, but also in all kind of engineering fields. And definitely the insurance agencies are best client for this kind of analysis. When we have the explicit limit states and limit state function that clearly define the below and above what is the failure criterion, it's easier to do it numerically, like integral of the limit state function, and see do you have the exact formula of the damage. Monte Carlo simulation is one of these also useful for the analysis. In this example, characteristic is actually used both either Monte Carlo and direct integration modeling, and it showed all the advantages. So it's not actually a question which method reliability will use. It's important just to know this kind of philosophy and to apply it whenever it's demanded in order to better communicate with our clients, with the society, with the insurance agencies. Usually we engineers, we just need to fulfill some codes, but other people who are not engineers, they need some different kind of information in order to be able to understand what are the risks on the particular projects. Thank you very much.